Hi everyone, thanks for coming. I'm Roshan. Many of you know me, and if you don't, you should come up and introduce yourself later if you want to. So this talk, it's called Predicting Rewards at Every Time Scale. And I phrased it in this way because I want to sort of bring it back to reinforcement learning. But in general, this work is about, you've got a sequence of things going on in the future, and you want to predict or, you want to estimate those things at different time scales, right? So this is work in progress, right? This is just all of this is still happening. It's not a finished story by any means. This is actually very similar to what Craig was doing, if you remember his tea time talk from like a month or so ago. This work was partly inspired by Chris's tea time talk, like one of the first tea time talks this summer. So this is like you're being dropped right in the middle of the story here. So lots of gaps, but Okay. So like I said, so in reinforcement learning, we often care about timescales, right? So if you've seen Patrick's work and similar things, or things like Horde, right? You might want to estimate the rewards you're going to get at different timescales, right? So if you've got a long-lived agent, the agent might want to know how much reward it's going to get in the next minute, but it might also care about the next week or the next the month or years or whatever, right? And very often these quantities are interesting for various reasons, right? So you might have policies that do different things based on when you are going to get a certain reward, right? So yeah, and this is just like a little picture of like different time scales that show up in our lives. So yeah. Okay, so I'm just going to dive straight into this. In reinforcement learning, one of the signals we care about a lot is reward, right? So I'm just going to define this thing called R of t, and that's the expected reward t time steps from now, and given that you're starting at some state S0, right? And for now, I'm just going to fix that state, right? This doesn't really matter. This is just to simplify the presentation, but you can do this at all the states that you care about, right? So for now, just imagine a sequence of numbers stretching out in the future. There is nothing random about this because each number is just the expected reward that you're going to get t time steps from now, right? And so I define this function R of t. And for the rest of this presentation, I'll just be using R of t, right? You don't need to worry about the fact that they're rewards or they come from a Markov process or anything like that, right? So this is just a stand-in for a time series that we have. Okay, and then you can define this thing, right? You can define the n-step returns, which are just the sum of the first n things in that series, right? So sorry, this should be t equals 0 to n minus 1 of R of t, right? So just add up the first n rewards, right? And so this is one way of imposing a time scale, right? So if I ask what's a 100-step return, so I call this an n-step return, so then that's just telling me how much reward I hope to get in the next 100 steps, right? Another way we have of talking about timescales in reinforcement learning is with discounting, right? So you can pick gamma, a constant between 0 and 1, and then you can add up all of the rewards from 0 to infinity, but you multiply each reward by gamma to the t, right? So let's say gamma is something like 0.9. So then the first gamma is going to be gamma to the 0, and then this next one is going to be 0.9, and then 0.9 squared, and so on. So you are giving more weight to rewards that are in the immediate future and less weight to rewards that are far away, and the weights are dropping off sort of geometrically, right? So and then people will often say that when you have a gamma discounted return, then that's acting on a time scale. Sorry, I guess my battery died. So that's acting on a time scale something like 1 over 1 minus gamma, right? And the reason for that is because you can think of this as a process where you are flipping a coin with a certain probability, and that's the expected number of coin flips before the process terminates, right? So in some intuitive sense, this is measuring reward on a certain time scale, right? Okay, so now here's the problem that I set out to solve, or set out to see what you can do about. So let's say that you don't just pick one gamma, but you learn this v gamma for several different gammas, right? So you're learning gamma discounted value functions for several different gammas. So you can think of this as probing this future sequence of rewards at different time scales, right? So not just one time scale, but you just come up with some set of gammas, right? And the question that I want to answer is, if you have this information, you know v gamma for different gammas, how much does that tell you about the entire sequence of rewards in the future, right? So for example, if you know that v gamma is big for a small gamma, but small for a big gamma, that means you're going to get a lot of reward in the immediate future, but then not much reward very far from now, right? So that's kind of the intuitive understanding we have, but how much can you like quantitatively analyze about the reward sequence if you have this information, right? Yeah.
This is for a fixed policy. We're not finding different policies for different gammas.
Yeah,
Fixing a policy.
right. Right, so all of this is in the prediction setting. So you're just getting a sequence of rewards, there is no control. But all of this actually extends quite easily into the control setting. So you could do things like off policy and stuff. I'm not, like, this talk is not going into that. One thing I should say is that here, for the purposes of this talk, I'm assuming that you know what those V gammas are. We can estimate these things, right? So if you have a TD algorithm, you can estimate what your rewards are going to be in the future. So you might not actually have the exact values, you might have estimates of them. But this is all, this is just to answer this very simple question of if you have a few numbers like that, what does that tell you about the entire sequence of rewards, right? So let's see. So yeah, we might want to estimate the undiscounted n-step returns, right? That would be one thing you might care about. Or you might want to estimate V gamma for a different gamma that's not one of these gammas that you have in your set, right? So both of these questions are like asking, how does my reward behave at different time scales that are not necessarily the time scales that are by any of these gammas, right?
One more question.
Yeah.
It's a stochastic process, right? So there might be different trials for the same gamma,
right,
same type, but you might have different trajectories.
Exactly. Yeah. So it is a stochastic process, but I sort of waved away the stochasticity by taking expectations everywhere.
So suppose we had an expected value. So
yeah,
imagine it's deterministic is what you're saying.
Exactly. Yeah. Yeah. So yeah, and if you have a stochastic process, then like a Markov decision process, you might have an estimate for future gammas, but based on the past and stuff like that, right? So yeah. Okay, so here's sort of an example of what I'm talking about. So I just made up a sequence of numbers, 10,000 numbers, which I'm calling rewards. Each of those numbers is normally distributed with 0 mean and standard variance 1. And this blue step, the blue curve is the n-step returns from that, right? So this point, for example, is the sum of the first 5,000 rewards. Right, so this curve goes up and down. The rewards can be positive or negative, and so it's kind of telling you the cumulative reward I've earned up to this point, right? And the red dots are telling you the values, right? So they're telling you V gammas for 10 different gammas. Now the y coordinate of each red dot tells you the value, right? It tells you like how big the value is. The x coordinate of each red dot tells you the horizon. So it tells you 1 over 1 minus gamma for that V gamma, right? So this red dot is a very sort of short time scale V gamma, and it's it's got a very high value because you get a lot of reward like in the beginning, but then you end up with a bunch of negative rewards, and so the long time scale gammas are smaller, right? So so for the rest of the talk, all the algorithms I'm going to be talking about, they take the y coordinates of these 10 points as input, right? They take 10 numbers as input. For all these experiments, I just fixed 10 as a number of things I care about. So the question I'm trying to ask is, given these 10 numbers, how much can I recreate, how well can I recreate that blue curve, right? So how well can I recreate the n-step rewards for all the n's in there? So how do you solve this problem? It seems like a lot of information to get back because that time series had 10,000 steps in it. And how can I recover those 10,000 numbers from 10 numbers, right? So it turns out that you can do some estimations. You can use linear algebra to solve this problem. And I'll pose the problem and I'll tell you how you can solve it. So all the quantities that we're interested in here, they are all functions of time, right? So you got R, which is a function of time. It takes t and gives you a number. You got g, which is the cumulative reward for the first t time steps. That's also a function of time. Takes a t and gives you the reward after that much time. You got gamma to the t, which is also a function of t, right? So all of these objects are functions that take numbers and give you real numbers, right? So function from n to r. And I want to do linear algebra on these objects, right? So you can think of these objects as vectors in infinite dimensional space. And I'm going to define an inner product on this space, right? So given two functions like this, I'm going to say f dot g is the sum from 0 to infinity of ft gt, right? It's just a generalization of your standard inner product, but on infinite dimensional spaces. And this actually gives you a norm, right? So in, like the standard definition of a squared norm of a vector is the inner product of a vector with itself, right? And that's just the sum from 0 to infinity of the squared f of t's, right? Okay, so I have inner products, I have norms, I have a vector space, so I can use linear algebra, right? So now it turns out that if you think back to what the definition of a gamma return is, it's the sum from 0 to infinity of ft and gamma to the t. And that's just the inner product of rt and gamma to the t. So that's just the inner product of the r function with the gamma to the t function, right? For different gammas, gamma I to the t. So you can think of this as taking this vector, this infinite dimensional vector, and projecting it into lots of different basis vectors, right? So the original vector you started with is r, and the basis vectors are like the gamma to the t vectors for the different gammas, right? And there's k of them. So in this case, k is 10, sort of in the graphs that I've been showing. So this is a system of k linear equations. And I can't solve the system directly because it's got an infinite number of unknowns, and I only have k equations. But I can solve it in a least square sense, right? So what I'm going to do is I want to find a linear combination of these gamma functions, gamma to the t functions. So the coefficients are c1 to ck, right? So I want to say c1 times gamma 1 to the t, c2 times gamma 2 to the t, and so on. And these are all functions of time, right? So I'm taking a linear combination of these functions of time, and I'm going to use that as my estimate of the reward function, r hat, right? And c is the coefficients in that linear combination. Does that make sense so far? So that's kind of the problem that I want to solve. And I want to find a c that minimizes this distance. It minimizes the distance between the real reward function, which I don't know, and the r hat estimate, right? So I want to find the estimate that minimizes that squared distance. And the distance is again that thing that I defined in the last slide, right? Okay. So it turns out that this problem is quite simple. This is linear regression. It's just you're just doing it in sort of a finite dimensional space that's embedded in an infinite dimensional space, but that doesn't really cause any problems. So you can actually solve this in closed form. It turns out that the coefficients are, there's a matrix called capital K, K inverse, times the vector of all of these values that you have, right? So these things are all known. They depend on a reward sequence. You multiply that by the inverse of that matrix, and that gives you the coefficients you need, right? So this is actually just another form of the linear regression problem, right? I have to tell you what K is. So it turns out K is a matrix where the ijth entry is the inner product between the ith basis function and the jth basis function, right? So this is the sum from 0 to infinity of gamma I to the t times gamma j to the t. And it turns out you can solve that in closed form, right? So that's just an infinite sum. So that is like you can solve this, and it's just this number, right? So far, all you need to do is you need to construct this matrix, calculate. So somebody's given you this set of gammas. You populate the matrix with these numbers, invert that matrix, and you're off to the races. The important thing to remember is that this K matrix does not depend on the problem in any way. It doesn't depend on the rewards. It doesn't depend on anything except the set of gammas that I've picked. And this vector is the only thing that depends on the actual sequence that I'm seeing, right? So if I wanted to solve this problem again and again for different states, or if I wanted to solve it at every time step, I don't need to invert K or calculate K again and again. I can just calculate K once, the beginning of my problem, and go from there, right? Okay. And now we have these estimates. We can estimate other things, right? So now I have an estimate r hat of the rewards, so I can estimate the n step returns. Just add up the first n rewards, right, of my estimate. You can actually do this in closed form because this r hat is a linear combination of exponential functions, and there's a formula for adding up the first n terms of an exponential series, right? You can just do that. You don't actually have to do the sum from 0 to n minus 1. You can estimate gamma returns for other gammas that are not part of the set. Again, just remember we said that the gamma returns are the dot product of the reward function with one of these gamma to the t functions. So you can do that dot product. And again, you can evaluate this in closed form in constant time because there's a nice, it's just the math simplifies, so you don't actually have to do this dot product because r hat has such a nice form. It's a linear combination of exponential functions. Okay, and what happens when you do this? It turns out that you get something like this green line. So this green line is a result of this algorithm that I just talked about, right? And it's supposed to be a reconstruction of that blue curve, but remember that it's based on just those 10 numbers, those red dots that come here, right? And you can see that it's actually quite a faithful reconstruction of at least the sort of the gross form of the function. It doesn't capture all of the little wiggly details because when you're computing gamma returns, that's actually a very smooth function, right? If one reward changes quite a bit, that doesn't because it's an average, right? It's a weighted average. So all of these little variations, high frequency variations in the time series are not going to affect that very much. So you are in effect getting a smoothed version of that function, which is a linear combination of exponential functions, right? So so any questions about this so far? Okay, so this kind of answered my basic question, which is how well can you reconstruct the original function given these 10 numbers, right? And then the other question I asked was like, how do you estimate the gamma return for other gammas that is not in your set, and that's what this pink line is. So each point on this pink line is a gamma return for one of the gammas that lies in between the red dots that were part of my input, right? So you can think of this as perfectly interpolating the gamma return, right? I do want to sort of make one comment here, which is that very often, if you care about, let's say, the 100, the reward on a horizon of 100, very often people will calculate like a gamma corresponding to that horizon, and then they'll compute the gamma return, right, of the reward for that. But that's actually very different from the reward on the first 100 time steps, right? For example, if you look at this dot, this is supposed to be a gamma return for a gamma which corresponds to this horizon, but it's very far away from the actual reward that you got in that many time steps, right? So I mean, so this is not saying anything new. I'm just pointing out that taking a weighted average with a gamma weighting that's on expectation 100 is not anywhere close to computing the reward for the first 100 time steps. Okay, so that's pretty much like as much as I wanted to say. There's a lot more directions that you can take this. And in fact, some interesting ones which I'll briefly get into. But the major open question that I have not addressed is, I assumed here that you know the exact V gamma, right? And any realistic setting like in RL, you don't know that. You have estimates of it based on what you've seen in the past, and you're estimating into the future, right? And so that still raises the question of how accurate this reconstruction is going to be. The inputs are not exact, right, if there's noise in them. I have reason to believe that that is actually not such a big problem, because the way that matrix is constructed, it has sort of it's a very well conditioned matrix, so it's not going to be highly perturbed if you add noise, but that's still something I have to experiment with. And here's the other thing that I didn't really say. So it turns out that I didn't do this work in the way that I presented it. My inspiration for doing this work was actually recognizing that when you have a sequence of rewards and you compute a gamma return, that's actually computing a Laplace transform of that sequence, right? So there's this thing called a Laplace transform. It's similar to a Fourier transform, if you heard of that. A Fourier transform is taking a signal and figuring out sort of how much of a periodic signal is there in it, right? So projecting it onto a basis of sines and cosines. Here we are doing the same thing, except instead of sines and cosines, we're using exponential functions, right? So decaying exponential functions. So that was actually my inspiration for getting into this, because this looks like a Laplace transform. And what we are computing here is sort of an approximate inverse Laplace transform, right? It turns out you cannot compute an exact Laplace transform computably, because you have to evaluate an uncountable integral, but we can do it in this approximately squares way, right? But apart from that, the Laplace transform has a lot of interesting properties. So there's a variant of the algorithm here that I just talked about, that I didn't talk about. So the algorithm that I talked about here was you estimate the reward function, right, r hat, and then if you want to estimate the n-step returns from that, you just take partial sums. You add up the first n's estimated rewards, and that gives you the n-step returns, right? And that's actually an integration operation, right? You start with some signal and you integrate it. You get a new signal which is the sum of the first n steps in that signal, right? And so what I did here was I started with a Laplace transform, inverted the Laplace transform, then integrated the estimate that I got from there. But you can do this in the opposite order, because it turns out that if you have a signal, you can do the integration in the Laplace space in sort of, you don't actually have to compute the integral. It's just a pointwise transformation of the Laplace function. So you can do the integral and then do the inverse Laplace transform. Gives you a different algorithm. I've plotted the results of that algorithm here. That's this orange, whatever, gold line. And I don't have theoretical justification for why you might use one algorithm over the other. But I just wanted to point out that when you recognize that you're dealing with Laplace transforms, you can do all sorts of interesting things based on the properties of the Laplace transform, right? So these are some interesting questions. I'm going to stop here just to show you like a few extra things. So that K matrix that I mentioned, the reason I call it K is that it's a kernel matrix, right? This whole thing is a kernel trick. And the properties of this algorithm depend a lot on what that matrix looks like. So I should, how do I, okay, sorry, just give me one sec. So I've plotted here what that K matrix looks like. So the diagonal entries are all 1 because I normalized everything. The basis of functions that I'm talking about is not orthogonal. If it was orthogonal, all of diagonal entries would be 0. But these functions are actually highly correlated with each other, the gamma to the t function for different gammas, and so you don't quite get like a white and black matrix. You get a lot of correlation, but that's fine. That's what the matrix inversion takes care of, right? It sort of reverses that correlation. And then if you want to sort of like I can like show you what it looks like on different signals. So if you have a different signal, for example, then you get gamma. You get gamma returns that look like that. Yeah, and then you kind of get these, different. So you get like reconstructions of the signal that kind of, as I said before, they follow the growth shape of the signal, but they kind of smooth out the, the fine noise in them, and different algorithms. So yeah, so that's the end of my talk. It was quite informal. Like I said, it's a snapshot of work in progress, but happy to take any questions if you have them. Yeah.
So my earlier question, if you want to learn a policy, so if you have the policy which optimized for gamma equals 0.9, that's very different than policy optimized for gamma equals 0.7 or 0.5.
So actually, I used to think that, but then I read the latest edition of Rich's book, where he shows that like if you take a policy that optimizes for 1 gamma, then if you change the gamma, you still have the same optimal policy. Yeah, so it doesn't actually, so changing gamma just applies a scaling factor, but it does not affect the ordering of policies by optimality under that gamma.
So the optimal policy is the same?
The optimal policy is the same, yeah. And in fact, the gamma return is just going to be a scaled version of the gamma return under the different gamma, yeah.
This is for a continuing task, right?
It actually doesn't really matter. I don't really care whether it's a continuing task or episodic task or whatever.
The order of policy changes if the task is episodic.
Oh yes, it is for a continuous task, and if you have a stationary, stationary distribution under that policy, etc. Yeah. Anything else? Yeah.
If you have more and more gammas,
yeah.
Can you prove a consistency that you recover the original signal?
You won't actually. So I can actually do this interesting experiment here, where I can just do this. I was hoping somebody would ask. So let's say instead of 10 functions, I make as many functions as there are things.
Perfect, right?
No, I'm spoiling it, but it actually doesn't. Maybe yeah. So it's taking a little while to plot that the kernel, but I'll spoil it. It actually looks very similar to what you have with 10 functions. The reason for that is because all of these gamma value functions are very, very smooth, right? So no matter, like even if you have lots and lots of gamma functions, you're not reconstructing sort of the tiny variations in the signal because you're averaging them all away.
So
I should have, okay, maybe I shouldn't have picked 10,000. So that is an interesting question, right? So as you add more and more functions, you're not necessarily increasing the fidelity of your reconstruction. So there is some sort of inherent smoothness that the problem has, and you can't get more variation than that. However, this is where I'm going to give a shout out to Chris, because in Chris's tea time talk, he talked about using complex gammas, right? And when you have complex gammas, then gamma to the t is not an exponentially decaying function. It's like a sinusoidal function with an exponential decay, right? So now your space of basis functions is not just made of these exponential decaying functions. The problem with exponentially decaying functions is they're very, very smooth. So when you take a linear combination of them, the result is also going to be very smooth. But if you throw in a few, sinusoidal functions with different frequencies, then you can reconstruct all sorts of details in the original function, because you have this basis of functions that allows you to do that. And all of this math should go through. Just throw in a few complex gammas in the mix. I don't trust my code enough to try it just now, but in principle, it should all go through. And so that raises an interesting point of what is a good basis of functions, right? You can have different gammas, but you can also have complex gammas, so periodic functions, decaying functions, etc. And that gives you more representable power in the space of functions you're coming up with. I wanted to make another point, I guess I should have paid somebody to ask me this question. But but the point I wanted to make is that this is actually very similar to what happens with states, right? So when you have value functions, they are functions of states, and when you're doing function approximation, you have a basis of functions of states, and you take linear combinations of them, right? You're doing linear function approximation, and you might do something like tile coding. And tile coding, you might have tiles of different resolutions, so that allows you to reconstruct resolution, like different resolutions in the state space, right? Everything we are doing here is the same thing, but happening in the time domain. So instead of thinking of the value function as purely a function of state, you think of it as a function of state and time, and then you have function approximation on this state space, but you can also have function approximation on the time domain, right? And that's kind of what we're doing here. So so in a longer version of this talk, I would spend a few minutes talking about how you should unify space and time and function approximate both of them together, because then you can actually get things like you can have an algorithm that learns to use different gammas effectively for different parts of the state space, right? So if you have a part of your MDP where things are branching out a lot and lots of variation, you might choose to use a different gamma to make good approximations. But yeah, Kenny, yeah, I think you had a question.
Oh yeah, so does it go to the same function in the limit? Like if you go way higher than 10,000?
No, it will never go to the same function.
So in what sense is it even an approximation?
It's an approximation because you are taking the original function and you're finding a prediction of it onto a particular subspace that minimizes an error. The problem is the subspace of functions we're talking about can only represent smooth functions. Right? So one way to fix that would be to make that space richer by allowing it to represent more kinds of functions, and then you will be able to get closer and closer to the function that you care about. Another direction that you I haven't really talked about is that if you have these V gammas for a bunch of different gammas, I'm using that same set of gammas as the basis of the space I'm expanding in. Just because it's convenient to do that. But that's not necessarily, you don't necessarily have to do that. In some cases, you can pick a different set of gammas that is better for expressing your function than you have available in your value functions. But yeah, I'll leave it at that. I guess there's another point which I should also have paid somebody else to ask, which is that all of these exponentially decaying functions, their problem is that they are exponentially decaying. They all go to 0. So any linear combination of them is also going to go to 0 eventually, right? So in some sense, and then the another problem is that you kind of trade off resolution, because these functions, they vary a lot in the short time scale, right? Like if you look at the immediate future, all of these functions look very different. But when you look far in the future, they're all basically 0 functions, right? So whenever you have a technique like this, you are gaining a lot of resolution in the immediate future and not much resolution in the far future. That might be something you want, right? Because in general, you do care more about rewards that are in the immediate future rather than in the far future. But there's another approach to solving this problem, which is that, remember I wrote down an inner product, which was just the sum of ft's for all t from 0 to infinity. I can actually put a weight on these. So I can have sum of ft, gt, and some weight that depends on t. And I can choose that weight in different ways. So for example, I can choose that weight to be square root of t, or 1 over square root of t. Or I can choose the weight to be e to the minus t with some constant. And it turns out that even with those modifications, you can compute that kernel in closed form, because people have worked out what those sums are in closed form. And that might allow you to do things like explicitly say that I care about time steps 1,000,000 steps in the future to something like the square root of 1,000,000, right? This might happen because, because when you add up 1,000,000 rewards, you're going to get more variance than when you add up 10 rewards, right? So you expect a signal 1,000,000 time steps in the future to have more noise, and so you might want to weight that differently. I've done some experiments with that as well, and that works fine. So yeah.
I find it really stupid to have that weight decaying in the first 100 and then back to 1 again, or back to 1,000, back to 1 over,
right,
number which is 1,000.
Yeah, if you had like periodic weights or
which increase in amplitude. So I think the 1,000 in the future now counts the same as something right now.
Right.
Does that? I mean, that makes the world weird, right? That means I care.
Well, so that's kind of what happens in the default case, right? So in the default case, there is no weighting. The thing that I showed now,
but it goes down. I'm saying have a weight which the weight
goes up. Right.
Goes up in a way that cancels out some of the decay over time.
Yeah, so that's one of the things I thought about. It does cause some stability issues, and I don't know how well that works, but you can make that work somehow. Right, so one of the things you can do is, instead of estimating the signal you care about, you can estimate a decayed version of that signal. Instead of estimating r, you can estimate r times gamma to the t, and then you can just remove that gamma to the t after you've done that estimation.
But I'm saying, if multiply whatever gamma is in T. So a thing like where I care about the future more than the present.
Yeah, yeah. So that's like one of the things that's possible, and yeah, it's something I have to try.
It's
and
a weird world, but
yeah, yeah. So yeah, that's a
what I
yeah. So I guess another interesting point that's kind of different from linear regression is that in linear regression, you have two things, right? You have a true function, you have the estimated function, and you have the distance that you're minimizing, right? In this case, you are minimizing the distance to some linear combination of functions, and you've decided what that subspace is. But the distance function you're using is totally independent of the gammas that are part of that basis of functions, right? So when I wrote that argmin of yeah, I guess it's too much work to go back to that presentation. But when I wrote that argmin, right? So I had an R and I had an R hat, and I was minimizing the distance between them. And the definition of that distance did not depend on the gammas or anything. It was just like this squared norm thing, right? So that's kind of an interesting property. It means that you can do a lot of things with the basis functions, but without screwing up the problem, because you don't have a weird distance, which often happens in other kind of linear regression problems. Yeah. So any more unpaid questions?
Does it ever converge?
I think it's just hanging trying to plot that graph. So all of these computations are actually really quick. They take fractions of a second. But plotting, for example, is something that we still have problems with. But yeah, thank you.